Sure, yeah. I think this is turned on. Yeah. Aren't they fantastic?
Good afternoon. It's good to have you all here at Southwestern Adventist University and for the Wright Science and Religion Lecture Series. This is our last lecture in our series for this academic year, and I've seen many of you at some of our previous lectures, so thank you for being here. The topic tonight, or this afternoon, is the miracle of mathematics. And maybe you're thinking because you passed mathematics, that was a miracle in the first place. I don't know. But that will not be the topic today. And I'm glad you came out. I'm a mathematician. I love the title of the lecture this afternoon. And I think as you get to know our speaker just a little bit, he has a lot of energy. He's a bright young man, and he loves the subject of mathematics. And he has a way to bring that to the level of everyone in the audience. So hopefully you will be able to walk out of here and say, I learned something unique and special today. So what is mathematics? Why does it work? How does mathematics apply to the real world? What we're going to do today, or what the speaker is going to do, is investigate a few mathematical topics that are beautiful and bizarre. So I'm looking forward to that. His education, he got his bachelor's degree from Stanford University, and most recently, about 3 years ago, he received his PhD in mathematics at Wright University. His research is on knot theory. Yeah, so some of you are excited about that. Some of you have no clue what that is. Maybe he will give us a hint of what knot theory is. If I look down at my shoes, I knotted my shoes before I came. I don't know if that has anything to do with knot theory. But that's one of his research areas, as well as low-dimensional topology. Our speaker is an assistant professor of mathematics at our sister school, Andrews University in Berrien Springs, Michigan. I had an opportunity to meet our speaker in January at a non-math meeting, and I was very, very impressed with our speaker. He has a lot of insights about a lot of things related to our church, and I'm really looking forward to his talk this afternoon. Let's give a warm Texas welcome to Dr. Anthony Bosman. Welcome, sir.
Thank you so much, Dr. Shaw, and the opportunity to be here at Southwestern. You have a beautiful campus. I was exploring it this afternoon. Such a friendly community you have here. And so I'm thrilled to be with you. Howdy. I'm happy to be back in Texas, able to say howdy. What I want to talk with you today is about the miracle of mathematics. And I want to suggest that there are 4 features of mathematics that are simply miraculous. No, it's not just that you passed math class. And it's not just that somehow a few of us even went on to get full degrees in math, but somehow embedded in the activity of doing mathematics, if we step back and look at what it is to do math, we're going to see a miracle unfolding before our eyes. And so what I want to do is begin exploring this first feature of mathematics. And that first aspect of mathematics that's just absolutely miraculous is that we can do math. We can do it. Maybe you question this, but trust me, we can. And so let's do some math together. We're going to begin simple with just 1. You guys know 1, right? And from 1, we can go on and build up 2 and 3 and 4, and we call these the counting numbers. For good reason. They're the numbers we use to count things. How many sheep do I have, right? Or how many late bills do I have? We have these counting numbers. Now, they might seem easy, but already we've made a big jump. How many sheep do I have? I moved from a physical sheep to something called 1. And somehow this thing called 1 describes both the sheep and the number of markers in my hand, and the number of people on the stage, and the number of whiteboards on the stage. There's a level of abstraction here that's pretty sophisticated. Where did this abstraction come from? We have emerging research that shows that from the time you're born, you count. That is, counting isn't something we teach our kids to do. It's something they're born with an innate ability to do. Yes, we have to teach them the names for 1, 2, 3, or in some other language, maybe uno, dos, tres, or whatever it may be. We teach them the words for it, but the idea of number is innate. Think of it this way. Just as a baby is able to tell the difference between blue and red, children are able to detect the difference between one object and 2 objects and 3 objects. From as young as 2 days old, a baby can identify if there's 2 objects in this collection, or when it changes to 3 objects, or when it changes to 4 objects. There's a small region of their brain that recognizes number. I believe that this is evidence that we are all born with the ability to do mathematics. That is, you're hardwired to do math. Maybe you didn't realize that about yourself, but all of us are born math people. Now, as you know, mathematics gets a little bit more sophisticated than just 1, 2, 3. There's another number I want to show you now, a number that's caused immense controversy throughout the history of mathematics. This number is 0. What's so controversial about that? How many sheep do you have? 0. It doesn't seem controversial, but wait a second. What did I just do? I counted a sheep that doesn't exist. Somehow 0 is counting things that don't exist. How am I able to put a name on the non-existent, right? Just to see how controversial 0 is, think about the dates, about the years. We are in right now 2020 AD. If we went all the way back, we'd be in 1 AD. What was the year before that? 1 BC. There is no year 0 because the ancients were very uncomfortable with this idea. In most ancient civilizations, when they came across the idea of nothingness, recording that there were no sheep, they would just leave it blank. Or in some cultures, they would write out the word nothing, nada, none. It wasn't until rather late that we actually developed the symbol for 0. And it took quite a while. It wasn't until the 1700s that it was widely accepted throughout Europe. And so, of most of our history, 0 was very controversial. But you know that there are even more interesting numbers. I'm going to show you now one of my absolute favorites. It's so great, you can even put it on socks. That number is pi. You know pi. What is pi? It is 3.141515936897932384626433883793383832795028. It goes on and on and on and on and on, right? Where does this number come from? Well, you take a circle, you measure its circumference, you divide it by the diameter. Okay, seems simple enough. Wait, any circle? I did it for that circle. Does it work for a bigger circle? Yeah, any circle. Measure the circumference divided by the diameter. That's a little bit surprising. That for any circle you pick, if there's a constant there, the fact that pi is constant is surprising. But we go on, pi, it never ends. It's a funny kind of number. You can't write it as a fraction. Maybe you've learned pi is close to a fraction. It's almost 3 1/7. That's a decent approximation, but that's not quite what it is. We call these irrational numbers, right? It's like if you needed any evidence that math can be irrational, here comes pi. But it's not the only irrational number. You might have learned about some other irrational numbers. One of my other favorite irrational numbers is e. Have you ever heard of e before? This comes up all the time in connection to the calculus. E is a surprising number. Here's one way to define it, my favorite way to define e. You take 1 and you divide it by 1. Then you add to that 1 divided by 1 times 2. So what do we have so far? This is just 1 divided by 1, 1, plus 1 divided by 1 times 2, 1 divided by, that's 1 1/2. I have 1 1/2. Then I'm going to add 1 divided by 1 times 2 times 3. Do you see where I'm going with this? Okay, so here I have 1 over 6. I'm going to add that. Let me keep going. Plus 1 over 1 times 2 times 3 times 4. And we're going to keep adding more and more. I've ran out of space, but we'll keep doing this forever. We're going to keep adding more and more and more pieces to it. Well, wait a second. You want to add up infinitely many things? That's allowed? Well, it's okay. You have some hope it's going to work out because each piece is getting smaller. 1, 1/2, 1 over 6, 1 over 24. Then it'll be 1 over 120. The pieces are getting smaller, so you're just adding a little bit more each time, but you still keep adding more and more and more. What happens? Does it go off to infinity? No, it stops at this number E, this number that's about 2.7182818. It goes on and on forever as well. We get an irrational number called E. So these numbers show up throughout mathematics. 1, 2, 3, 4, counting, 0, counting, pi, that shows up all the time in geometry, but other places as well, like statistics, quite surprisingly. E, essential to our study of the calculus. Now there's one more number, though, that is truly bizarre. You might say it's not even a real number, it's an imaginary number. How many of you guys remember the number I? The square root of -1. The imaginary unit. Now this is quite a bizarre number. Typically when you take a number like 3 and you times it by itself, you get out a nice positive number like 9. Or -3 and you times it by itself. Well, a negative times a negative, it's still positive. But here's a number that when you times it by itself, I times I gives you a negative number. We call it an imaginary number. It opens up a whole new world of mathematics called complex numbers. There's some beautiful things there. This is probably where you start checking out in math class, right? Imaginary numbers, what? So you have these different pieces of mathematics coming from all different fields, from just counting and arithmetic, from geometry, from calculus. This arises in algebra and solving polynomials and finding roots of polynomials. All these different numbers popping up in mathematics. But then something happened. In the 1700s, a mathematician by the name of Euler made an incredible discovery. He discovered that these numbers fit together like pieces of a puzzle. So he said, notice what happens. You take that E, you raise it to the ith power times pi, you add 1, and you end up with 0. This was Euler's discovery, and it shocked the mathematical world. What? They all fit together like pieces of a puzzle? How is this possible? Well, what is going on here? We didn't think about this. We were just thinking about circles and adding fractions and taking square roots and negatives, but somehow all the pieces fit together. We have done studies that show that when mathematicians look at this equation, right now, Dr. Loga, Dr. Durarte, and Dr. Shaw looking at this equation, the emotional centers of the brain are lighting up. The studies show that when mathematicians see this, it's the same response as when normal people see a sunset, a beautiful painting, listen to a great piece of music. It's evoking an emotional response. Something is going on here. We see this as beautiful. It's considered the most beautiful equation in mathematics. How are we to make sense of this? What is the significance of this? Euler didn't start off as a mathematician. Euler was the son of a Christian minister, and originally he went off to college to study theology. He studied Greek and Hebrew and was getting ready to go into theology. But then a mathematician by the name of Bernoulli met him, began mentoring him, was able to redirect him, convince his father, it's okay, you can go into mathematics, you don't have to do ministry. And Euler changed paths to go into mathematics. So glad he did, or else the world may not have known about this equation. But Euler, although he moved to mathematics, He always maintained a high view of Scripture and a strong conviction for the truthfulness of God's Word. And so for Euler, him doing mathematics had some kind of spiritual significance. In particular, in the 1700s, there was an atheistic movement that was arising out of France called the Freethinkers movement. And these freethinkers would critique Scripture. And one of the ways that they criticized Scripture was they would point out supposed contradictions. Oh, this gospel account says this, but this gospel account puts it this way. Isn't that a contradiction? It must not be true. Euler was very bothered by this. But Euler responded. He wrote a pamphlet called A Defense of the Revelation. And in this pamphlet, he made an observation. He said, you think you found some contradictions? Well, when doing math, all the time, I come up against supposed contradictions. Let me give you an example of a kind of contradiction you might run into when doing mathematics. You could begin with the number 0. 0 is 1 minus 1. You with me? Okay, that's pretty good. Let's add another copy of 1 minus 1 to it. Each of these is 0, so the sum is just 0. And that's fine, so you could keep doing this. You could keep adding copies of 1 minus 1. But then you might come along and say, wait a second. 1 minus 1 plus 1 minus 1 plus 1 minus 1. Let's instead of think about that, there's a 1 at the beginning here. And then what am I doing to that 1? I'm going to subtract 1, and then I'm going to add 1. I'm going to subtract 1, and then I'm going to add 1. Yeah, subtracting 1 and then adding 1. And now do that again the next time. I'm going to subtract 1, and then here there would be a plus 1. And so by just moving the parentheses around, this is the same thing as 1 plus minus 1 plus 1 plus minus 1 plus 1, and so forth. We just move some parentheses. But notice what we get. 1 plus, what's minus 1 plus 1? 0. And minus 1 plus 1? 0. Oh, it's just a bunch of zeros. So we've just shown that 0 is actually 1. That would be a problem, right? Like, something seems to be a contradiction in mathematics. We could give many more examples of these supposed contradictions. So here's Euler's response to the atheistic critique of Scripture. He writes in his defense of the Revelation, he says, I could produce several examples here, but the least I can say with assurance is that these apparent contradictions are much more significant than those that are supposedly found in the Holy Scripture. I mean, 0 equals 1. You can't get much worse than that, right? He goes on to say, despite this, no one suggests dismissing the certainty of mathematics. This doubt doesn't even exist in those who have the capacity required to refute this. Even if you can't find what's wrong with this, you would say to yourself, well, I know somewhere there must be some mistake in this reasoning, so you're not going to go out and throw out all of mathematics. Euler is suggesting that that should be our attitude towards faith as well. Just as in mathematics, you may come up against some sticky problem. Oh, did I show 0 equals 1? No, there must be some mistake in my reasoning. Let me go back and check. Let me wrestle with this for some time. We don't just dismiss all of mathematics. Euler is saying the same is true for faith. Don't just give up on all of faith because there's seemingly a contradiction, seemingly a point of tension. Hold on to your faith because there's some really beautiful stuff there you don't want to give up. But I want to suggest in a similar way that this observation of Euler can continue to serve as a kind of apologetic today. Just like how in the 1700s, Euler is responding to a critique of faith that had arose. Today, in the 21st century, this observation that mathematics works, the pieces fit together, serves as a powerful apologetic. In an essay written in 1960, Eugene Wigner pointed out that mathematics is unreasonably effectiveness. He calls this the unreasonable effectiveness of mathematics. And in this essay, he argues this is suggesting something. We should take this seriously, the fact that we can do mathematics. Listen to his observation. He says, the great mathematician fully, almost ruthlessly, exploits the domain of permissible reasoning and skirts the impermissible. doing things like irrational numbers, imaginary numbers. They're going to the boundary of what is rational. They're going to the boundary of what you're allowed to do with numbers. Wigner goes on, that this recklessness does not lead the mathematician into a morass of contradictions is a miracle of itself. The fact that we don't end up with just a bunch of contradictions, but we actually get out this beautiful result, like e to the I pi plus 1 is 0. He says that's a miracle. But listen very carefully to how Wigner continues this article. Certainly, it is hard to believe that our reasoning power was brought by Darwin's process of natural selection to the perfection which it seems to possess. Wigner is pointing out that we're so good at reasoning, mathematics evidences this, that it's difficult to explain how that could arise under naturalism alone, how that could simply be the result of some unguided naturalistic process. How could it be possible that we'd come up with the ability to do this incredible mathematics? Things that people have been working on for hundreds and thousands of years, building together to these glorious results. Why would they lead us here rather than just to a complete contradiction? The mathematician John Lennox at Oxford University, he puts it this way. He says, ask someone, where does your brain come from? Give us an account of the history of your brain. Go all the way back. Where did it come from? And if all they have is a naturalistic account of how it arose out of some unguided process, of how it was the result of non-purposive system, then ask them, well, why do you trust it? Why would you trust your brain? Why would you trust your thoughts? Wigner and Lennox and others are pointing to this fact that the deep reasoning we're capable of doing is suggesting maybe there's something more about what it means to be human. We'll come back to that theme in a few minutes. But first, I want to discuss with you the second miraculous aspect of mathematics. It's not just that we can do mathematics. Rather, it's that the mathematics we do turns out to be exactly right for describing the world around us. That is, we can say math describes the universe. I was recently walking around Bayou campus, the beautiful library that you have here. And I was imagining, if you were a dog sitting in this library, what would your experience be like? You'd probably have many eager students come up and pet you, and you would enjoy that, right? Lots of good stuff to sniff out. But you would be blissfully unaware of the books all around you. Well, maybe you would see that those are nice things to chew or something, right? But you would never think to open a book, and let alone attempt to read it. A dog's mind is simply not wired to make sense of the content of those books. You following? Yeah? But how fortunate it is that we find ourselves in this library of the universe, and we can go out and study the universe and open those books. And what happens when we do? We find the contents describing the deep structure of the universe. We can read them. It's written in a language we can recognize. That language is mathematics. Why is it that mathematics is so appropriate to describe this deep structure of the universe? Let alone, why can't we even make sense of the universe? Einstein put it this way. He said, the most incomprehensible thing about the universe is that it is comprehensible. It's incredible that we live in a world that we can make sense of, that we can find these fundamental laws that allow us to make predictions and model how the universe acts. Why can we do this? If we look to the history of mathematics, math and physics have long been tied together. Many of the great mathematicians were also great physicists, astronomers. They developed the math in order to explain the world around them. People like Einstein and people like Newton developing the calculus in order to model motion. And so it makes sense that, okay, we built math in order to explain this universe. But let's ask a more fundamental question. These pioneers of modern science, what gave them the audacity to expect that they would be able to go out and find laws of nature? Why is that something you would think you could do? You know, it's a kind of a weird way to spend your weekend, right? Now, you've all grown up and you've learned in physics classes and various math classes that these laws exist. But go back 300, 400 years, before we've developed them. Why would we expect to be able to find such laws? C.S. Lewis, accounting the history of science, puts it this way. He says, people became scientific because they expected law in nature. Why? They expected law in nature because they believed in a lawgiver. Isaac Newton was many things. He was an awesome mathematician. He was a physicist. But first and foremost, he was a theologian. For Isaac Newton, his primary concern was to understand how God was acting in the world. And for him to go out and study physics, and for him to go out and study mathematics, were expressions of him seeking to understand who God is and what he was doing. So you've heard the story, that one day Isaac Newton was sitting under an apple tree, and an apple falls at Isaac Newton's head, and suddenly, the law of gravitation, universal gravitation, that the force between two objects is the gravitational constant times the mass of those forces divided by the radius between them squared. You familiar with this? The distance between them squared. This law of gravitation, this universal law, that we can both now understand how objects move in the heavens, why the earth orbits the sun, and why apples fall down. But this was not the source of Isaac Newton's insight. It's not that an apple fell on his head, right? That's not going to do anything but give you a bump. What Isaac Newton's fundamental conviction came from was Isaac Newton studied Scripture and had a strong conviction that the heavens and the earth were created by one mind. And if there's one mind that's behind both heaven and earth, then we should expect one description for both how objects move in the heavens and how objects move on the earth. Prior to Newton, there were these views that there was one set of laws for the celestial and another set of laws for the terrestrial, things on earth and things in heaven. But by unifying the two, it was an expression of Isaac Newton's conviction that there's a single mind between the two. So he expected there to be some consistent principle, a consistent principle he expressed mathematically in his universal law of gravitation. But something really curious happens. It's not just that Isaac Newton was able to find such a law, but it's that his law turned out to be accurate. You see, at the time, Isaac Newton didn't have very good data he was going off of. You know, it was the 1700s after all. They didn't have the most sensitive equipment. And so based on the data he had, when he looked at this law, it was 96% accurate. That's pretty good, pretty close. But you would think that over time, you would need to tweak this and refine it to get it more and more accurate. But instead, the opposite happened. Over time, when we got better and new data, the law stayed the same, and the data started conforming to it. It's this weird curiosity that happens again and again in the history of physics. We find some nice equation. Oh, that's quite nice. I would like it to be true. It's not quite fitting the data, but the equation's nice. And then, well, give it some time, and now we go and do the calculations. It's 99.999999% accurate, right? It fits the data very, very closely. This has happened so often in the history of physics that a number of physicists have begun commenting on it. One is the physicist Dirac. He says, a theory, a nice model, with mathematical beauty. Look at the simplicity. You just do some multiplication, some division. It has nice symmetry to it. A theory with mathematical beauty is more likely to be correct than an ugly theory, something with ugly mathematics, that fits some experimental data. He goes on to argue, God is a mathematician of a very high order. He has used advanced mathematics in constructing the universe. If you have to choose between nice math but not quite fitting the data, and some ugly equation that fits the data better, probably the nice math is correct. Because somehow the universe has a beautiful elegance in its mathematical structure. That's what Dirac and others are arguing. Back to Wigner. This essay of Wigner, it's not just on the unreasonable effectiveness of mathematics. The full title of it is The Unreasonable Effectiveness of Mathematics in the Natural Sciences. What Wigner is pointing out is he says, there's something really surprising here that mathematics is able to model the universe so well. He concludes his essay this way. Listen to the language he uses. The miracle. 12 times he uses that word in this essay. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. Again and again, mathematicians and physicists are pointing to this fact that we can do mathematics, that we can explain the universe. This is some kind of incredible gift. But I want to suggest there's one more aspect of mathematics that's perhaps even more miraculous. It's not just that we can do math and that math describes the universe, but it's that pure math is useful. What do I mean by pure math? An applied mathematician is someone who goes out and says, I want to model this physical phenomena. And so what I'm going to do is I'm going to go and find something in my mathematical toolbox to make sense of it. They're good people, but I am a pure mathematician. I am someone who says, forget about reality. I just want to do math. And so what I do is I try and develop new math for the sake of doing math. It's probably why they put us down into the basement. It's like, you don't need windows, you have blackboards. You don't need reality, make your own reality. And it's true, for us, the blackboards are the windows into our mathematical realities. And so when someone comes up and asks me, so this math you do, what is it good for? My response is, hopefully nothing, right? Like you wouldn't go up to Michelangelo and be like, oh, so I hear you paint ceilings, right? Like, no, it's not like I'm doing like painting houses to be functional. I'm making it because it's beautiful, right? And so the pure mathematician sees her job as less a functional job and more of creating something like poetry, something for us to enjoy, for something for us to relish. But here's the sad reality. As much as I don't want my math to be useful, the history shows that time and time again, it is. That is, we try and come up with math that's just really far out there and bizarre, and then suddenly, 80 years later, some physicist comes up and he goes, yeah, that describes reality. I'm like, no, I was just trying to do math. And so I want to tell you one of my favorite mathematical stories that illustrates this, so you can see how this has played out in the history of mathematics. And the story I want to tell you is the story of geometry. So perhaps at some point in high school, you recall learning about geometry. And the way geometry is built up, the way Euclid built up his geometry, is he began with 5 simple axioms, 5 statements that we're going to build everything up from. These are the rules of the game, that once you have these down, we're going to build up everything from these 5 simple statements. The first simple statement was that if you have 2 points, you can connect them with a line. That seems fair. Second statement, if you have a segment of a line, you can extend it as far as you like in either direction. The third statement is if you have a point anywhere and some distance, you can make a circle with that distance as its radius. Maybe here's a point, maybe you want a further distance, you can make a bigger circle. We can make circles, very nice. The fourth observation is that, well, maybe I'll come over here and make a right triangle, and maybe my buddy will come over here and make a right triangle, but those will still be the same size. Both will be 90 degrees, we would say, in our modern language. The idea is wherever you draw a right triangle, it's going to be the same angle. And then the fifth one, if you have a line, and you have a point somewhere, well, you could draw some lines to that point that hit the other line. But there's one special line you can draw that's parallel to the other line. So you can draw parallel lines. So these are the 5 basic rules of Euclidean geometry. And from these, in this beautiful work called The Elements, Euclid goes through and he discovers all kinds of incredible things from just these 5 foundational stones. He builds up incredible facts about geometry. So one of those is a fact about triangles. Using these, he's able to build up to the fact that anytime you have a triangle, no matter what it looks like, if you take the angles of that triangle, let's call these angles, say, alpha, beta, and gamma, and you add those angles together, do you remember what you get? 180 degrees. Any triangle, which happens to be 2 right angles, so that's quite nice. You add up these 3 angles, and it gives you 180 degrees, which is 2 right triangles. And you say, okay, I remember this. Yeah, that's geometry. But mathematicians started playing around with this. They started looking at these axioms, and one of them stood out. We looked at the last axiom, and we said it looks kind of awkward, kind of clunky. Given a line and a point, there exists a line through that point that is parallel to the first line. That sounds a little awkward. This first 4 is so much simpler. You can connect 2 points with a line. And so mathematicians started asking, well, do we really need this last axiom? Like maybe we can show this axiom from the first 4. Maybe we can build it up from the first 4 facts. No, that wasn't successful. Well, is there any way to get rid of that axiom? What would happen? Can we get rid of it, throw it off? No, this is just them playing games. This is what happens if we change the rules to the game. What if we change chess so this piece moves this way instead of that way? This is just playing games, not thinking about physics. And so they're like, yeah, I think we can. Actually, we can discover a geometry that doesn't follow that 5th rule. Incredibly, we've been standing on it this whole time. A sphere like the Earth. Yeah, you can draw points, you can connect them with lines, but are there parallel lines on a sphere? Let's find out. You can draw some line on the sphere. But what happens if you try and draw a line parallel to it? What's it going to end up doing? It's going to hit it at the North Pole and at the South Pole. On a sphere, this 5th axiom fails. You don't have parallel lines because all of your lines running up and down will meet at the North and South Pole. No longer is it the case that given a line and a point, there's always a line parallel to it. Because here, any line that goes to this point will hit this other line eventually. The sphere gives you a non-Euclidean geometry. And so what are the consequences of breaking this 5th rule? Well, if you break the rules of the game, it's going to have consequences for all these things we built up on that. If you crack the foundation, the whole system's going to fall down. In particular, triangles. Are they still going to add up to 180 degrees? Let's find out. Let's say we start building a triangle. So you go on a trip, you go up from the equator to the North Pole, and we're going to make a right angle. So we're going to turn 90 degrees. We are traveling up, we're going to turn 90 degrees. And then we travel down to the equator. And then when we hit the equator, we're going to make a right turn and meet up with where we started. So we go up, we make a right turn, we go down, we make a right turn, we go over. How many right angles do we have here? There's one up here, there's another one here, there's 3 right angles. What happens when we add those 3 right angles together? On a sphere, instead of a triangle adding to 180 degrees, on a sphere your triangles look kind of fat. They look like this. It's like they've been eating too much. And so now, when you add up the angles, instead of it giving you 180, it'll come out to be some number that's bigger than 180. For us, it was 270. Depending on the triangle, maybe a little bit smaller, but it's always going to come out to be a number bigger than 180 degrees. Something strange is happening on this sphere. But mathematicians weren't content to leave it there. We get to the 1800s now, and they're thinking, oh, let's really mess with the rules of this game. Let's really see what damage we can do. The sphere has curvature. Yeah, it curves around. And you may think, okay, if I have a small sphere, it'll be quite curved. But if I have a large sphere, like a planet, when I'm standing on it, I don't even notice that it is curved. The bigger the sphere, the less I notice the curvature. That is, if I have some radius r, the curvature is given by 1 over r. So when the radius is really small it's a bigger number, but when the radius is really big, the curvature is less noticeable. The curvature is 1 over r for a sphere. Well, that's just the curvature in one direction. It also curves in this other direction. So we say, on a sphere, the curvature is 1 over r times 1 over r. Because you have two different ways that it's curving. So we end up with curvature of 1 over r squared. Now, you know that when you square a number, it's going to come out to be positive. A number times itself is a positive number. So 1 over r squared is going to be some positive curvature. But mathematicians started thinking, wait a second, is there any number that you can square so that it's not positive? Is there a number that you times by itself to get a negative number out? What is that number? We talked about it at the beginning, I. If you plug I in, I squared gives you -1, right? So if there was a sphere that had an imaginary radius, it would end up having negative curvature. A sphere with imaginary, now you know the mathematicians have gone wild, right? Like we are not even trying to stay attached to reality. We're saying, let's introduce spheres that have imaginary radius. Like what? How can you even imagine that? But the mathematicians did. And here's what they imagined. A pseudo sphere. It's a sphere that has constant negative curvature. Like the ball, but instead of the curvature being positive, now it's negative everywhere. We call this a pseudo sphere. And notice what happens. Crazy things happen on a pseudo sphere. What would a triangle look like on here? If you had a triangle, the sides would come up and they would meet. But try and visualize what that triangle would look like. Your triangle, the two sides would come up and meet. It would look something like this. The third side would come around. It would look something like this. What do you notice about that triangle? This triangle was a fat triangle. It had extra angle. This triangle is a little bit skinnier. All the angles a little bit smaller than you expect. So now when you add up alpha, beta, and gamma, what do you think is going to happen? Instead of it coming out to be something more than 180, like here, because it was fat, it's going to be less than 180. Alpha plus beta plus gamma comes out to be less than 180. And so mathematicians were just excited because it's, wow, we don't just have one geometry, the geometry of the plane. We can introduce spheres, or these pseudo spheres is what it's called, where we can have zero curvature, or positive curvature, or negative curvature, and each one gives rise to a different geometry. I said this was happening throughout the 1800s. And it would be fine. That you would think that these are just them up in the ivory tower doing what they do. But then we entered the 1900s, and there's a guy by the name of Einstein, and he's thinking about reality. I don't know why, but I guess physicists do this. And when he's thinking about reality, he says, wait a second. What if reality isn't like the Euclidean picture? What if space-time is curved? What if mass curves space-time around it? And that's where gravity comes from. And so what Einstein does is he uses these non-Euclidean geometries to give a description of space-time. And since Einstein, we've been able to verify that, in fact, this happens. That massive objects like the sun actually curve the space-time around them. So rather than it acting in a Euclidean fashion, it works in non-Euclidean ways. There's curvature to space-time. What is the moral of the story? Mathematicians were trying to just play games, trying to escape reality, doing things because they were pretty neat and kind of cool and maybe even a little bit beautiful. And yet, when they then step back and let the physicists think about the world, it turns out the mathematicians made just for fun turned out to describe reality. What do these first three miracles about mathematics tell us? We can do math. Somehow we're hardwired from the time we're born to think rationally. That math describes the universe. And even when we're not trying to describe the universe, even when we think we're just playing games and pursuing truth and beauty, it turns out that truth and beauty also describes the universe. What does this tell us? We've seen that for the naturalist, one that merely has a naturalistic account of the world, it's very difficult to make sense of this. But if you have a biblical understanding, in particular, if you accept the doctrine of creation, that there was a God who created humanity in the divine image, now it's beginning to make sense why we're rational. That same God is creator of heavens and earth. Now it's beginning to make sense why there's an order and there's a structure to the world. And the God that created us is a lover of beauty and truth. And so us being made in his image, when we seek after beauty and truth, we find that goes on to describe the world as well. There's a deep sense in which doing mathematics harmonizes with the biblical picturing. Some, like David Hume, philosophers, have critiqued the idea of miracles. How could there be a miracle? Isn't that a violation of the laws of physics? Isn't that a violation of natural law? But wait a second, David Hume. The very fact that there are laws of physics and that we can know them and describe them mathematically, that in itself is a miracle. I want to suggest the miracle of mathematics harmonizes deeply. It helps us, it fits well with the Christian picture of creation. But there's one more miracle that I have to tell you about, because this is the one that gets me buzzing. This is the one that gets me excited. And it's not just that we can do math, that math explains the world around us, even when it's pure math. But it's the fact that mathematics never ends. Math is endless. And I know what you're thinking. That's not very exciting, right? Like, oh no. I remember sitting in math class, counting down the minutes and being like, okay, 10 more minutes of this, or one more math class, 2 more. But I'm going to show you that mathematics, it's very exciting. And the fact it never ends is signaling, it's suggesting something that's utterly profound. I told you the story of geometry. Let me tell you a very similar story, but now about arithmetic. So just like how geometry begins with some simple axioms, so does arithmetic. There are these axioms of arithmetic. And these axioms, we could say, for example, the piano axioms are a common set of axioms that you begin with to build up arithmetic. These are axioms that just say things like, there's a number called 0. So just like in geometry, how you say there are points and lines and circles, there's a number called 0. And there's a number after it called 1. And there's a number after it. And there's a number after it. And it says after each number, there's another number. And these numbers are different. 0 is not equal to 1. I'm going to avoid that mess from before. So those axioms just give you these basic principles. And then we can go on and we can define things like addition and multiplication. And we lay this down as a groundwork. And then we begin building up arithmetic. We can start asking questions like, some numbers are kind of nice. We'll call some numbers prime numbers because they have a special property that you can't divide it out into two smaller numbers, right? So you remember the prime numbers. They're numbers like 2 and 3, but not 4, because you can break down 4 as 2 times 2. So that's not going to be prime. It's numbers that you can't break down into two other numbers times each other. And so what would be the next prime number? 5, and then not 6, because it's 2 times 3, so the next one is 7, and then 11, not 9, because it's 3 times 3, and then 13, yeah, we're good. Not 15, that's 3 times 5. 17, that'll work. 19, what's next? Yeah, not 21, that's 3 times 7, but 23 will work. Not 25, not 27, but 29. 31. There seems to be quite a few of these guys. But they seem to be thinning out. They're becoming a little bit less common. How many primes are there? Well, that's a good question. How many primes are there? Well, it's a question the ancient Greeks engaged with. It's one that Euclid asked. Did you know what Euclid discovered? How many primes are there? 17, 18? Infinitely many. They never end. There are infinitely many primes. And some people make a whole job out of trying to find the next one. They program these big computers and try and calculate the largest prime that they possibly can. It's the basis of our modern security. When you buy something on Amazon or when you do a transaction, your information is protected by big primes, so you should be grateful to them. But it's a good question, but there are other questions we can ask. Another question that came up in the 1700s, in 1742, a man by the name of Christian Goldbach asked a question about primes. He said, I noticed something. When I take an even number, not 2, but beginning with 4 or 6 or 8 or 10, I'm always able to write that even number as the sum of 2 primes. So example 4 is 2 plus 2. Yeah, those are both prime numbers. How about 6? 3 plus 3, yeah, those are both prime. How about 8? Oh, that's going to be tougher. It's not 4 plus 4 because that's not prime. Oh, you could do 3 and 5, or you could do 2 and 7. There's a couple ways to do it. How about 10? Yeah, 3 and 7. You guys are rocking it. How about 2020? Well, you can think about that. He noticed this pattern. He wrote to Euler, and he said, Euler, is it true that you can always write an even number as some prime plus another prime? And Euler's response, it is certainly true, but I don't have time right now to prove it. But it's certainly true. I can't figure out why, but I know it's true. This was back in 1742, I said. Since then, we've tested a couple evens to see if it's true. In particular, we've tested 400 trillion evens to see if it's true. And it's held up. But how do we know that the 400 trillionth and first even, it doesn't hold for? Maybe we need to do 500 trillion, or maybe 600 trillion, or a quadrillion. We want a proof. Just like how Euclid was able to prove that infinitely many primes, so we don't have to go out and find them all, we want to prove that this works for all of the evens, because we can't check it by hand. And so we've been trying since 1742 to answer this question. We're still working on it. We don't know what the answer is. If you can go and prove it, that'd be great. Let me know. We can split the credit. But something happened in the 19th century where a mathematician by the name of Gödel notice there's something interesting that happens mathematically. What Gödel did was he was able to take a statement about mathematics and encode it into the language of mathematics. Let me show you that statement. Gödel took the statement, this statement cannot be proven by the axioms. Gödel took this statement and using a clever way of encoding the statement into actually prime numbers, he used prime numbers, he was able to encode this into a mathematical statement. Now, why is this significant? Step back and think about the statement with me. What would happen if we proved the statement? What if we could prove the statement? Well, then we have proven a statement which has a cannot be proven. What would that give you? That would be a paradox or a contradiction. If we prove the statement that says it can't be proved, that would be a contradiction. That would be like me saying, I'm lying to you, and you able to prove that I'm telling the truth. That would be a contradiction. So what if we can't prove it? If we can't prove, that means there are some questions we can ask in mathematics that can't be proven. So in some sense, a mathematical system is incomplete. Oh no. We're either going to run into a contradiction or a mathematical system will be incomplete. Now that might be quite distressing to you. That we start out with these axioms, we start asking questions, but maybe there are some questions we could never answer. Maybe Goldbach's conjecture is one of those statements. We don't know. Maybe it's the case that we'll never be able to give an answer to Goldbach's conjecture from these axioms. But it's not such a bad scenario, because look closely at the statement. It cannot be proven by those axioms. So what do we have to do? Well, we have to add more. We need to add some extra axioms. And when we add extra axioms, now our mathematical universe grows by a little bit. And those questions that we couldn't answer before, we can now answer. But then you know what happens? New questions pop up. And those we're not able to answer with the axioms. So what do we have to do? We need to grow our axiomatic system even more. And our mathematical universe grows a little bit further. And in this way, mathematics becomes inexhaustible. Gödel didn't show that mathematics is uncertain or that there's some kind of lack of clarity in mathematics. Gödel showed we'll never stop doing mathematics, because the act of doing mathematics will raise new questions that require us to grow our mathematics to answer those questions. But then it's just going to bring us to new questions, and it's going to keep growing and growing, and so we're never going to be done. Mathematics is not something just done by the Greeks thousands of years ago. It's something we're still doing, and something we're going to need eternity to exhaust. Reflecting on this, the late physicist Freeman Dyson expressed his desire that this isn't just true for mathematics. Freeman Dyson put it this way. He said, Gödel proved that the world of pure mathematics is inexhaustible. No finite set of axioms or rules can ever encompass the whole of mathematics. Given any set of axioms, we can find meaningful mathematical questions which the axioms leave unanswered. I hope, this is Freeman Dyson's desire, I hope an analogous situation exists in the physical world. If my view of the future is correct, it means the world of physics and astronomy is also inexhaustible. No matter how far we go into the future, there will always be new things happening, new information coming in, new worlds to explore, a constantly expanding domain of life, consciousness, and memory. So Freeman Dyson is looking to the future, and he says, just like how mathematics is never ending, is inexhaustible, I hope the same is true for our study of the world around us. When I read Freeman Dyson's quote, I think to myself, wow, the Christian hope for eternity answers that desire in his heart. His longing for an ever-expanding opportunity to know the world. If you read the book Education by Ellen White, the last chapter, it's fantastic. She begins by writing, heaven is a school. Its field of study, the universe. Its teacher, the infinite one. I believe that just as how mathematics is inexhaustible, so we'll be spending eternity doing it. I know you might think that sounds more like hell than heaven, but we'll be doing it for eternity. We'll be growing mathematics. So too, we'll be growing our knowledge and discovery of the natural world. And most exciting of all, it will take eternity, just like mathematics, to come to understand and know the love of God in Christ. It's a subject that we'll never be able to exhaust. That each time we think we've come to understand God's love, it's going to get even bigger. It will get to the boundaries of that, and it grows more. Oh, there's so much more I can say about eternity. But let me close with that vision. This sense that just as how mathematics is a miraculous thing, that doing mathematics gives you a little taste of eternity, a little desire that I wish I could do this forever, that a whiteboard becomes a window into eternity. It awakens a desire in your heart and lets you know that likewise, for eternity, we can be studying the God of order behind this all and his incredible love. I think we'll pause now and we'll have a few questions. Yes? I'll tell you my favorite definition of mathematics, and you won't like it. Mathematics is that which mathematicians do. It's a serious definition that's been offered, but now you're going to have to ask a second question. What is a mathematician? You're going to like my definition even less. A mathematician is one who does mathematics. But it's the only definition I can offer right now. I can offer some generalities that mathematics is about finding patterns, but just because throughout the history of mathematics, it's grown so much. I mean, the work I do now in low-dimensional topology, I work on the boundary of 3- and 4-dimensional manifolds, really out-of-this-world stuff. It looks nothing like the mathematics the Greeks did 2,500 years ago, right? It's very different. You can trace a thread that, okay, similarly we use deductive methods in order to make inferences from simple first principles in order to make more complex theorems and propositions that build up and describe the structure of these abstract entities. But it looks quite different. And so I think I'm very much grounded in the fact that mathematics is a human enterprise. And so mathematics is something done by people. And those people kind of help give us the outlines of this is the boundary of mathematics, things within this or what constitutes mathematics. And so I can't really give you a definition that's totally divorced from the community of mathematicians. Yes?
I've heard it said in different ways that mathematics is the language of God.
Yeah.
So to your illustration of the dog in the library,
Yeah.
do mathematicians, Christian mathematicians,
Uh-huh.
let's say, ever feel as if they are exploring the mind of God when they're doing this open analysis? And then, what about the non-Christian mathematician? Where do they think they're exploring?
Yeah, it's a wonderful question. So there's a few different views on the nature of mathematics. One is mathematics is something we're discovering. So just like how a biologist goes out and observes things about the natural world and that constitutes biology, the mathematician is looking into some kind of mathematical universe, and we're describing it, right? And maybe perhaps you could say that mathematical universe is in the mind of God. This was one view. Augustine pushed back on this a little bit. How could we possibly know the mind of God, right? It seems kind of weird that we're knowing God's mind through rational inquiry outside of Scripture, outside of God's self-revelation. And so there may be some pushback on this. Philo had a little bit of a different view. He thought that God created a mathematical universe of ideas before he created the physical universe, right? This was Philo's idea. I don't subscribe to either one of those. I think mathematics is something that mathematicians do, but because we are people who are made in the image of God, our acting out of mathematics in some way reflects God's rationality. It's not us reading God's mind or God's thoughts. We are humans and we have creativity. And so my favorite example of this is that of a garden. Is a garden something that is created, or is it something that is discovered? And there's a sense in which a garden has an aspect of discovery. You go out into the world, you find the different plants, but human creativity allows for how we design that garden, how we decorate that garden, right? And so I think that there's a marriage of these two views in how mathematics is played out. Certainly, when we're doing mathematics, we often feel like these things actually exist. But I think when I stop and reflect what mathematics is, yeah, somehow it's grounded with laws of logic, but there's also a lot of room for human creativity. And so just like a poem or a piece of music, it's a human expression that doesn't exist out there somewhere, but very much is a product of human beings. There's a related question maybe I'll touch on. Maybe this will help clarify. There's this old youth world dilemma. Does God do something because it is good, or is it good because God declares it? You know this dilemma. You know, it's when God gives us a law, a moral decree, is that thing moral just because God said so? Or did God say so because God himself is subject to some law? And the way the Jewish and Christian theologians have wrestled with this is, I believe, pretty consistently they've concluded, well, neither. It's not that God is subject to some set of morality that's higher than him, and it's not that God acts arbitrarily and then that stuff becomes what is good. Rather, God acts from his nature. And since God's nature is the center, it's the locus of what is good, God is acting consistently with that moral nature. And I think it's similar with the laws of logic. It's not that God arbitrarily decreed laws of logic, which is the foundation of mathematics, nor is it that God himself is constrained by them, that there's some higher law that God's accountable to, but rather it's God himself is rational by nature. And therefore, his acts reflect that. His creative work reflects that rational nature of God. Yeah, we have a mic we can get you right here.
You mentioned, I don't know if it's even testing. Anyway, you mentioned that a sphere has curvature, like latitude, longitude.
Yeah, positive curvature, yeah.
Yes, positive curvature. And the pseudosphere adds one of them negative. Can you get a pseudosphere that has both negative?
Yeah, okay. So remember in our definition of curvature, we noted that it's not just curving in one way, but both ways. And it's the timesing of those two ways together that gives you always positive curvature. What's going on here is because it's curving in two different directions, one will be negative, one will be positive, but negative times positive gives you a negative. And so that's why it comes out to be negative. If you want to experience the pseudosphere for yourself, at least this kind of negative curvature, and you don't have a 3D printer, you can go buy some Pringles. And if you look at a Pringle, there's a similar thing going on. We call this a saddle. But one way it curves one direction, and the other way it curves the opposite. And so it gives you this negative curvature. And so you can draw little triangles on here, and you can calculate the sum of their angles, and you can do wonderful geometry on a Pringle. And then when you're done, they're really delicious.
In theology and certainly in the arts, we discuss God in terms of his transcendence and his immanence, and there's this, I know historically been some pendulum swing there. It seems like much of what you're saying with math, at least in my reasoning, speaks to the transcendence of God. But is there an aspect of math that is a great testimony to the immanence of God?
What a wonderful question. I have no idea how to answer that. Well, maybe this is the best way I can answer it. Maybe not in math as an abstract discipline, but as math as something that people do, right? Like people actually wrestling with this. And if you go back and you read some of the statements of these great mathematicians, Gauss and Euler and others, when they were wrestling with a problem, they were praying. they desired God to give them insight and clarity. And very much in some of their journals and reflections, you can see the sense that they believe that God was giving them wisdom and understanding, right? And so in their act of doing mathematics, it wasn't like a deist, God set this thing and he's far off and we're trying to understand it. But they thought God was very actively involved with them in that struggle. And let me tell you, like, you probably know yourself how emotional it can be to do mathematics, right? So frustrating. And imagine if this was your whole career and, some of these problems they spent many years working on. And so this was something that their whole heart and soul was into. And they saw that throughout the process of them wrestling, that ultimately God was the one giving them insight and was present in that. And so maybe in the experience of the mathematician, you have that sense of God being close by. Yeah, right down here.
Since you stated that you believe that mathematics and logic come from the nature of God himself, then would it follow that no matter what different universe God created, it would always share in common logic and mathematics?
Yeah, okay, that's a wonderful question. So I would say in some sense I think there's some core set of laws of logic that are reflections of the divine nature. Perhaps the law of non-contradiction. You can't have both P and non-P, right? You can't have something that contradicts itself. Even throughout Scripture, God seems to suggest this. I'm the God who changes not. I'm not one thing yesterday and another thing today and tomorrow, but I'm core to who I am. And that's important because if you have a contradiction, anything can follow. There's no consistency in your system. But I also want to emphasize that very much doing mathematics is very much a human thing that reflects human creativity. I mean, even the letter E is the letter E because it's named after Euler, right? But the way that we define our numbers, the way we build up our ideas, it could look very different if you had a different culture, a different civilization. The fact that we use base 10, right? That everything is a multiple of 10, hundreds, thousands, 10,000s, 100,000s, millions, is because we have 10 fingers, right? And so if it was a civilization of 8-fingered people, they probably would have done a different base, or some did. The Mayans had base 20, 10 fingers, 10 toes. The Babylonians used base 60. Maybe 6 of them got together, and then they're like, oh, let's do base 60. So you do have these kinds of variations across culture. And mathematics is, in many ways, an expression of the people who worked on it throughout history. So I don't want to deny that. But I do think there's some core aspect of logic, non-contradiction, some of these really foundational things that do seem to be reflections of a fundamental aspect of God's nature. Yeah. Bring the mic back here. No, that's great. Here we go.
Mathematics describes the real world.
Incredibly well, unreasonably well. This was Wigner's response. How well does mathematics describe the real world? The unreasonable effectiveness of mathematics in the natural sciences, right? Now, we don't always see it. It might take us some time for us to realize the application of some of this math, and maybe none of the math is describing this particular world. I mean, I work with 4-dimensional manifolds, these 4-dimensional universes, and our universe probably isn't any of those. But so there's a way in which mathematics can go beyond the constraints of reality when we abstract away. But this is Wigner's point that it's surprising how well math makes sense of reality, particularly in the natural sciences and the physics. In the social sciences, maybe a little bit less so, right? People are tricky, people are complex. And maybe we need to be cautious not to try to impose mathematics as the ultimate standard in every discipline. Sometimes other disciplines, the social sciences, feel like if they could be more mathematical, they may be more legitimate, but it forces some awkward things onto them, and maybe it's better for us to realize there are other inquiries of knowing, other ways of knowing as well. And so we shouldn't try and force everything to follow some mathematical measure, right? Even in a place like a university, we want to be accountable. We want to make sure that the things that we're striving for are things that we can measure. And so we want to have all of our goals and outcomes be things that we can quantify and measure. Seems like good, responsible leadership. But wait a second. I really care about some things that's really hard to measure, like the character development of my students. That's a really tricky one, or the faith development of the community. It's really tricky to measure that. And so if we try and force everything to be, well, it has to be quantified and measured, maybe we're going to lose out on some things that are really important. And so I don't want to overimpose. I respect other disciplines of having other ways of knowing, and we should recognize that's totally valid. We're making sense of history or understanding a document or understanding human interactions. We shouldn't require everyone to come to some mathematical standard. There are other ways to approach it and have legitimate knowledge as well.
My father was born in 1902.
Glorious.
And when he was a young man, he went to the Catholic seminary to become a Catholic priest.
Yeah.
In 7 years, he never saw the Bible.
Wow.
He was told that was not true. Later, he became a Seventh-day Adventist. And he has spent most of his life trying to figure out the Bible. He believed that the only true in this world is math.
Okay.
If you tell somebody 2 + 2 is 4, nobody's going to argue with you.
Yeah.
Based on that,
Yeah.
he dedicated most of his life trying to prove that the Bible was the truth mathematically.
I see.
And he tried to explain it to me, and I really did not understand. But you said something today that I've been looking for practically all my life.
Wow.
I did not understand all your numbers, really. But what you said, I did understand that math are infinite.
Yeah.
And my father died assured that the Bible was the truth because he proved it to himself mathematically.
Wow.
But he tried to explain it to me, and he left it in writing and all that, but it's so confusing, but to hear was clear. So I just thank you for taking a block that I had in my mind,
Yeah,
that you are sure that there is a lot of truth in math.
Yeah.
It proves that the Bible is the truth mathematically.
Oh, what a beautiful testimony. Thank you so much for sharing that. That's really touching. Yeah, and what incredible that we have that hope of eternity, right? That that hope that we can be reunited with those we love and do mathematics forever, but also enjoy the love of God for eternity. Yeah, that's really special. I see a couple hands back here. Maybe we can get a couple more questions in. Here we go. Yeah.
Do you think that if we've got a big enough telescope in the space away from our atmosphere, we'll be able to see the edge of the world or the universe?
Yeah, so there is a limit to the observable universe, that which we're able to receive information from light from. Right, there's light travels has a limit to how fast it can go. So there was a limit to seeing the edge of the observable universe. A big open question is we're not sure how much more there is beyond the observable universe, right? So there's a limit to what we can observe, no matter how big the telescope. There's a limit to how much we can observe. But it's a big open question of, does the universe go on indefinitely beyond that, or what the fundamental structure of the universe is? So that's a really hard question that people are trying to answer right now. Good luck. Yeah.
Is there a mathematical reason you don't wear shoes?
It's very comfortable to wear socks.
Also, recently the new sabermetrics in sports.
Yeah.
Where are you with that?
Yeah, I'm not a statistician. It's a really cool field. It's a really cool area, but it's not my area, so I can't say anything authoritatively on it. If you want my gambling advice, it's don't. Maybe we can do one or two more questions. I think I saw a hand, and then we can. Was there one more here? No. Great. Well, I believe. Oh, here. Did I? Fake hand. Great. Maybe we can call that a wrap.
Okay. Thank you very much. Actually a very inspiring lecture, so thank you very much for coming and being with us. I've got a couple quick questions for you, and they're just very simple questions.
Let's do it.
So tell me how a mathematician thinks about infinity and also about multiple dimensions and how God fits into that space. Have you thought about that?
Oh my. Here we go. You said it was a quick question, but nope. So, I really want to tell this story. Can I have 2 minutes for the story? It's a wonderful story. It's a wonderful story. One of my favorite stories. I just gave this to my students as a problem set, as an assignment. So if you're watching, here's the solution. Okay. So this would be the line of real numbers, right? So in the middle we have numbers like 0 and then 1, 2, 3, negative numbers, and numbers in between too. And so I want everyone here to just think of a number, pick one, secretly in your head. Just think of any number, any real number, not those imaginary numbers, any real number. Do you have one locked in? Okay, just shout it out, go. Great, okay, so I heard some, I think someone said 25 maybe, and I heard a 365 or something like this. And those were good. Most of you said numbers like this. Most of you said whole numbers, right? And yeah, okay. There's a lot of whole numbers on here. But most of the numbers on here are not whole numbers, right? Like there's lots of numbers in between that are not whole numbers. Like between 0 and 1, there's a whole lot of numbers that are not whole numbers. And so there's a whole bunch of fractions, like a half. Did anyone think of a fraction? Like a half? Or Now, there are other numbers that are in between that are not even fractions, that are irrational numbers, but that we have nice descriptions for. Like, someone said pi, right? Brings me joy. So someone said pi, and so that's a nice little irrational number. That's right there. But all these numbers have something in common. They're numbers you could think of because they're numbers we can describe. That is, I can give you a precise definition for any of these numbers and communicate to you what the number is. I can say 365 is, and you know what 365 is. I can give you a definition of pi. It's you take the circumference, you divide it by the diameter. Okay, so it's like, yeah, those are numbers you can describe. But if you take out all the numbers you can describe, pull them all out, and you arrange them in their own line, how long do you think it'll be? You said there's a lot of them. There's infinitely many. Yes, there are infinitely many. But compared to all the other numbers here, it turns out that almost all numbers are indescribable. That the vast majority of numbers, there's no description for you. There's no number of words you can use to give a precise definition for it. It's a really bizarre idea. It's like, why haven't I ever heard about these numbers before? Because no one can tell you about them, because they're indescribable, right? That's why we don't talk about them. Almost all of them. So much so that if you took out all the describable numbers, although there's infinitely many and they're wonderful and they're fantastic, it would just come out to be a single dot compared to the number line. All those numbers are compressed down. We say it has measure zero. That's a fancy analysis term. Measure zero compared to the number line. And I find this incredible, that although there's an infinite amount of numbers we've been able to describe, it still just pales in comparison to the eternity of numbers that we'll never have enough words to describe. And I think to myself, man, God's love must be like that. It's like so deep, and like we'll always grow in understanding, and we'll get like a deeper and richer and like more and more descriptions, and like it's gonna be great. We'll go for eternity, understanding God's love, but at the end of it all, it'll still just be like a measure zero comparison to the vastness of God's love that remains beyond measure. So I don't know if that's what you're looking for, but that's how I think about this.
Thank you very much.
Yeah.
Let's give him another round of applause. Thank you. So we're going to close with a word of prayer, and we do have a reception. We hope you stay by, and if you have any individual questions you'd like to ask Dr. Bosman, please stay by to ask him. So let's bow our heads for prayer. Dear Heavenly Father, we thank you for this afternoon. We thank you for this inspiring lecture, and we thank you for the gift of mathematics, that each of us have the ability to do mathematics and experience it here in the real world, and to just play with it in our minds. And we do look forward to that time when we can spend an infinity of time with you, and that we can experience your great love that will just grow and grow and grow. We ask that you'll give each person here that's participated in listening, that you'll give them a safe trip. In Jesus' name, amen.
Amen.